Rolling sphere. We have a hollow sphere of mass m and radius r, and it is sliding with a velocity v0 at the top of a frictionless tabletop between points A and B. So what we have is this guy moving here on a frictionless tabletop. As the sphere moves through a rough section, which it starts at point B, okay, so this will indicate a rough section, the friction force changes the sphere's motion from slipping to rolling with slipping and then just pure rolling. The moment of inertia of the sphere is I equals 2/3 mr squared, and the coefficient of friction is mu. Express the linear velocity of the center of mass of the sphere when it is rolling with slipping. So that's right at point B. What happens when it gets to point B? Express the angular velocity as a function of time when it is rolling with slipping, and again, right at point B. Then find the time at which the ball begins to rotate without slipping. So that'll be somewhere over here. Okay, we're not interested in the distance here, just the time. Express the linear velocity of the center of mass of the sphere as a function of time when it reaches point B, and that is when it starts rolling with slipping. The only force we have acting on the sphere in the x direction is friction. So we have minus F equals ma in the x direction. The friction force is mu normal, and in this case the normal is just mg, as the object is not moving in the up and down direction. So we have our acceleration, and of course it's negative because it opposes motion. We then use this first kinematics equation. We substitute in our value for a, and here's our answer. Express the angular velocity as a function of time when it is rolling with slipping. Now be careful, don't just take the velocity from the previous slide and use this relationship here, where omega would be v over r. You can't use that because the sphere is slipping. So we have to find another way to do it. So we will use the sum of the torques is equal to I alpha, and then we rearrange it so alpha is the sum of the torques over I. The only torque is provided by friction, and that's that R cross F. It is acting, well, the F is the friction force, and that is acting perpendicular to the line of action, so it's just going to be mu mg, all right? So because the sine of 90 is 1, so R cross F is just R times F. And then we substitute in our moment of inertia that was given, and here's what we have to work with. We start canceling like terms, and we find that alpha is 3 mu g over 2r. We now want to find our angular velocity, and that will be the initial angular velocity, which is 0. We add our alpha, multiply it by t, and here is omega. And note, that is not equal to v over r. Find the time at which the ball begins to rotate without slipping. Well, we have our two equations here, where we have the velocity, where it is rolling with slipping, and our omega, where it is rolling with slipping. But now that we know we want to find where it rotates without slipping, we can use v equals r omega. So what we're going to do is set equation A, the linear one, equal to r times omega, which is our equation B. So here is equation A. We're going to set that equal to r omega. Here's omega, and you can see it shows up over here. So you just cancel out some like terms here. You find that v0 minus mu gt equals 3 mu gt over 2, and then you solve that for v0, and then you just rearrange it to solve for time. And at this specific time, the ball will rotate, it will start rotating without slipping.